Welcome to the SoCal FTC Kickoff for CENTERSTAGE. Here we will cover an overview of the FTC VisionPortal. My name is Chris Johannesson, and my contact info will be on the last slide. With only 45 minutes, this will be a basic overview. This is our outline today, following the green highlights. We start by introducing the VisionPortal technologies and the access system used by AprilTag. VisionPortal is software built into the FTC apps, running on the robot controller and the driver station. It was introduced this summer with SDK version 8.2 and updated with today's new SDK version 9.0. VisionPortal manages the use of AprilTag and TensorFlow technologies. It does not include Vuforia, used in prior years for image recognition. There are 12 sample op modes to show you how to use the basic features of VisionPortal. The software works with a built-in camera on an Android RC phone and on a USB webcam, or multiple webcams. For AprilTag, VisionPortal uses software called EasyOpenCV, which last year some teams incorporated into their own code. This year, many features of EasyOpenCV are built in to the FTC SDK. This website listed at the bottom, ftc-docs, covers all of today's material in more detail. This slide lists the ways that the SDK uses these two technologies. This presentation will focus more on AprilTag since TensorFlow has been part of FTC for several years. An AprilTag is a square flat image, or visual fiducial. At a minimum, it can detect the ID code of the tag, but also it can estimate the pose. Pose is a combination of the tag's position and rotation relative to the camera. TensorFlow object detection recognizes a three-dimensional physical object. This year, either a white pixel or a red or blue team prop that your team creates. The software defines a bounding box, a colored rectangle around the recognized object, and the software can also estimate the heading or angle that the camera must turn left or right to point towards the detected object. The VisionPortal detects AprilTags in the family 36H11. This is a family of tags that provides an ID code ranging from 0 to 586. In this image, you see a colored border on the left tag, indicating it is a library tag. Its name and size are known by the software, and therefore a pose estimate is available. The tag on the right side lacks the colored border and does not provide the size, and therefore a pose estimate is not available. Again, pose has two components, position and rotation. With this slide, we discuss only position or displacement. The question is, where is the tag relative to the camera? Specifically, where is the center of the tag relative to the center of the camera lens? To describe this, we use an XYZ axis system with its origin at the center of the camera lens. That's the green star. The yellow star is located on the face of the AprilTag in its center. The x-axis is the positive distance to the right from the green star to the yellow star. The z-axis is the positive distance upward. The y-axis is the positive distance outward. We can't see that vector since it points directly away from us from the green star. How long is the y distance vector? Just long enough for the x and z vectors to touch the yellow star as they slide outwards. The VisionPortal gives these values in real distance units like inches or centimeters rather than pixels. The other component of pose is orientation or rotation. This is the same image as before, but here we will consider only rotation. The VisionPortal reports pitch as rotation about the x-axis, roll as rotation about the y-axis, and yaw as rotation about the z-axis. Imagine that the April tag is exactly parallel to the camera lens. In that case, pitch, roll, and yaw would be 0. Looking at this example, the tag seems to be rotated slightly about the z-axis only. So pitch and roll would be near 0, while yaw would have some negative value. Let's use the right-hand rule to see why it's negative, not positive. With your thumb pointing up along positive z, your fingers curl with positive rotation to the left. But this tag is rotated slightly to the right, so yaw is negative. To reassure you up front, we want to mention there are 12 sample op modes to help you start programming with VisionPortal. These samples are included for FTC blocks, OnBot Java, and Android Studio. This slide shows the 7 op modes related to April tag. The first 2 are the most common. The first one is the easy version using only default settings, so you don't have to work with the builder pattern. The second op mode is the basic version. It does use a Java feature called a builder to specify options or custom settings. The third op mode shows how to use 2 cameras, switching back and forth. The fourth op mode is specialized, showing how to optimize the brightness or exposure of the camera image. This one is available only in Java. The fifth op mode is a tool used in webcam calibration, which we will mention again later. The last 2 op modes at the bottom of the screen will also be discussed later. These are autonomous sample op modes that can drive your robot towards an April tag. This slide shows the 5 op modes related to TensorFlow. The first 2 are the most common. Listed first is the easy version, using only the default settings for TensorFlow, so you don't have to work with the builder pattern. The second op mode is the basic version, which does use the Java programming feature called a builder to specify options or custom settings for TensorFlow. The third op mode shows how to use TensorFlow with 2 cameras, switching back and forth. The fourth op mode shows blocks users how to specify the custom TensorFlow model that you created for your team prop, instead of using the built-in TensorFlow model for a white pixel. The fifth op mode is an example of April tag and TensorFlow being used in the same op mode. Again, we show you these op modes now, so you know there's an easy path to get started with the VisionPortal. Next, we will cover the programming needed to initialize these tools. Each vision processor needs to be set up, typically in the init portion of the op mode. Also, the VisionPortal itself needs to be set up or initialized before any results are requested by your op mode. Before diving into the code, let's review the steps needed for initialization. First, if you are planning to replace the existing default April tag library with a custom library, you would need to do that before working on the processors. Most teams will never do this. So let's jump ahead to step 2, which is to create the April tag processor and/or the TensorFlow processor. Each of these processors analyzes frames streaming in from the camera. There are many settings available using a builder. After that, we go to step 3, which is to create the VisionPortal itself to manage the overall pipeline. In this step, you will specify the processors that you created in step 2. Note that processors work independently from each other. Here there are many settings available for the VisionPortal, again using a builder. This slide used two terms common in vision processing, the word stream and the word pipeline. Put simply, the stream of camera frames is the input to the pipeline. The AprilTag processor is attached to an Easy OpenCV pipeline, which performs various steps in order to each stream frame. A similar process happens for TensorFlow. Let's start by discussing the AprilTag processor. Here's one line of code to set up the AprilTag processor if you can use only the defaults. Most teams should start with this. This slide shows the blocks version up top and down at the bottom the Java version. Notice there is no mention here of the builder pattern. The builder pattern is used by the SDK behind the scenes, hidden from the user. Builder is a Java pattern or structure for adding features or parameters finalized with the .build command. Such features are not modified later during an op mode. This example shows a custom AprilTag library being specified and 4 other AprilTag processor builder features, and there are others available. If you don't specify any library, the processor will include only the default library. Note here that this string of commands ends with the .build command, which wraps up the builder feature ready for use. This Java code is equivalent to the blocks in the previous slide. The builder pattern allows a much more streamlined format in Java, which we will see in the next slide. But first we can see here that the builder is created with the .builder command. The optional AprilTag library is defined, and the 4 settings are established, and we close out with the .build method. We look now at the more streamlined version of the builder. This is a chained version with these dot methods all in a row, culminating in the .build method at the end. This code is exactly equivalent to the previous slide's individual method calls. Here, the object myAprilTag processor builder was not created. The build was performed directly on myAprilTag processor. Next, we will create the TensorFlow processor. Again, here's one line of code if all the defaults can be used. Most teams should start with this. This slide shows the blocks version and down below the Java version. Again, there's no mention of the builder pattern. It's used behind the scenes, hidden from the user. Here's the builder pattern in blocks. This example specifies 4 parameters for the TensorFlow processor builder. There are many other options, but most others relate to custom TensorFlow models, which is beyond the scope of this basic guide. Note that this string of builder commands ends, as always, with the .build block. This Java code is equivalent to the blocks in the previous slide. Here we create the builder, set the 4 options, and end with the .build method. In the next slide, we will look at the more streamlined version, or the chained version. Here we see the 4 dot commands, followed by the .build. Here the object myTFOD processor builder was not created. The build was performed directly on myTFOD processor. After creating the vision processors, now we create the VisionPortal. Again, this is typically done in the init section of your op mode. Then your op mode can actually start reading and processing camera images, still in the init section and or after touching the start button. Here again is a single easy create block to set up the VisionPortal. The first parameter needed is always to specify the camera. Also needed is 1 or 2 parameters for the vision processors that you plan to use. The FTC blocks menu offers 3 versions of this block: April tag only, TensorFlow only, or both, as shown here. If your robot configuration includes more than 1 camera, then the blocks menu also offers another 3 versions, with a special camera called switchable camera. So FTC blocks might offer 3 or 6 versions of this easy create VisionPortal block. In any case, it's still just one easy block to set up the VisionPortal. Again, the builder pattern is used by the SDK behind the scenes, hidden from the user. Here's the Java version of the previous single easy create block. This method can accept 2 or 3 parameters. Here we see the camera being specified, and in this case, 1 April tag processor and 1 TensorFlow processor. Here's the regular way to set up the VisionPortal using the builder pattern. We see again the first 3 parameters that were necessary even in the easy version: which camera you plan to use, planning to use the April tag processor, and planning to use the TensorFlow processor. But there are 4 more purple blocks added with other features being specified. The first one is to set the camera resolution to something other than the default of 640 by 480. Webcams can support a wide variety of resolutions, and you are free to use any of those. The next purple block allows you to customize the streaming format or video format being used. The default for FTC is YUY2, but this year we are offering an optional compressed video format called MJPEG. This is helpful to conserve USB bandwidth if needed. These other options help manage the CPU load, and there are many more than these 4 available. Again, notice that this process ends with calling the .build block. Here's the Java version of the previous blocks for setting up the VisionPortal. Here we specify the camera, the processors, set the camera resolution, we set the streaming format or video format, and other settings as needed. Finally, the last line always is to call the .build method. Here's the streamlined or chained version of the builder pattern. This code is equivalent to the previous slide's individual method calls. Here, the object myVisionPortalBuilder was not created. The build was performed directly on myVisionPortal. Here again, we see the 3 common settings of camera, processor, the other 4 optional settings ending with the .build command. Next, we will cover the previews that are available on the Android devices. These previews let you see what the camera sees, along with any graphics overlay or annotation from a vision processor. Camera Stream is the camera preview available on the driver station. With the op mode in init, touch the 3 dots menu at the top right, then choose Camera Stream. This is not live video. Tap the image to refresh it. To close this preview, touch the 3 dots and choose Camera Stream again. A new feature is to touch the arrows at the lower right corner for a big preview. This is the big version of the Camera Stream preview. It fills most of the screen of the driver station device. You can touch the arrows at the lower right to return to the regular sized preview. Live View refers only to the RC preview, not the same as Camera Stream on the DS device. Live View appears on the screen of an RC phone. For Control Hub, which has no screen, you can use an HDMI cable to plug it in and see this preview, Or you can research and install software called Screen Copy, spelled SCRCPY. This allows you to view the RC preview or live view remotely on your laptop. This software Screen Copy, of course, is not needed for RC phones. Now we will look at the previews available for TensorFlow. Here, a camera stream preview shows a white pixel with its TensorFlow bounding box surrounding it. It also shows the model's name and the recognition confidence level. Here, the software has a 94% confidence that this is indeed a white pixel. Camera stream is the camera preview available when the op mode is in init. Again, you touch the three dots menu, then choose camera stream. Tap the image to refresh, and to close the preview, touch three dots, choose camera stream again. Touch the arrows at the lower right for a big preview. Touch the arrows at the lower right again to return to a regular size preview. Live view again refers only to the RC preview, not the same as camera stream. Here's a pixel preview showing a 91% confidence level. Live view appears on the screen of an RC phone, but live view is also generated by control hubs, even though it has no screen. Use an HDMI cable or install software called Screen Copy, SCRCPY. Now we will cover the metadata stored in each library tag. A library is a collection of April tags. Each library tag stores metadata, which is a collection of up to 6 fields of data of these data types. We've already talked about the ID code, a numeric value. Each tag also has a name, which is a text string. Each tag has a size, which is a numeric value, and the units of that size are expressed in the fourth data element, which can be your choice of inches, millimeters, centimeters, or meters. That linear distance unit is used to express the tag size, and it is also used to report back to you the estimated position once the tag is detected. The fifth and sixth fields are for advanced use. The fifth one gives the tag location on the field in the Java type vector F. And the sixth field gives the tag orientation on the field in the Java type quaternion. Advanced teams could use these last two fields for field-centric navigation, which is not covered in this overview. If you would like to access all of the library tags that are part of the CENTERSTAGE game, you will use the first method listed here, get CENTERSTAGE tag library. This gives you all 10 default tags in the game, with each tag having its 6 metadata fields. There are three April tags at the base of the red backdrop, 3 April tags at the base of the blue backdrop. There are 2 April tags on the red side of the audience wall and 2 tags on the blue side of the audience wall, for a total of 10. This summer, with release 8.2, there were 4 sample tags placed into the SDK, and they are still there. If you would like to obtain those 4 tags, you can use this second method called get sample tag library. This will provide you access to those 4 tags, each of which contains only the 4 basic metadata fields. If you would like to get all the tags with a single method call, use the third one called get current game tag library. This retrieves both the 10 default and the 4 samples for a total of 14 tags. These commands are available in blocks and Java. After the April tag processor and VisionPortal have been initialized, your op mode can begin tag detection. When a library April tag is detected, the processor can evaluate and provide over 30 fields of data. One piece of data that you will usually read is the ID code. The yellow arrow in this slide shows the block that provides the ID code for the designated April tag. Other blocks provide other fields available for that detected tag. Here is the Java code to retrieve and store a detected April tag's ID code. Again, the VisionPortal can provide over 30 fields per detected April tag if that tag's size was provided, thus making it eligible for pose estimation. In this slide, at the right, we see the .id command, and the equal sign performs an assignment of that value to a temporary variable called myAprilTagID code, declared here as type integer. Since the camera might see multiple April tags at once, retrieving any field is usually done with a for loop. The loop can process each detection one at a time. The op mode should take the desired action for each April tag inside the for loop, or store information for later action. In this example, the variable myAprilTagID code receives the different values of each detection, ending with only the last tag's value. This code snippet assumes that myAprilTag processor and VisionPortal have already been initialized, as described in previous slides. This is the Java version of the previous slide's blocks. Notice that the for loop first verifies that the April tag's metadata is present, or not null. And again, the comment at the bottom indicates that this is the exact place where you could have the robot take action based on the data being read, or you could store that information for later action. We move on now to camera calibration. For pose estimates, the RC phone camera or the webcam model needs calibration data for the resolution being used. If you don't have that calibration data, you will not get a good pose estimate. Fortunately, the FTC SDK does provide some calibration data for 4 webcams. The Logitech C270 has the data provided for the default resolution of 640 by 480. The Logitech C920 provides data for the default resolution and 5 others. The C310 provides data for 2 resolutions, and for the LifeCam, the default resolution has calibration data available. By the way, the Logitech C270 webcam can support 18 resolutions. The C920 webcam offers 19 resolutions. Teams can generate their own calibration data, which is called lens intrinsics. Lens intrinsics is simply a set of 4 numeric values provided by the camera calibration software. You will simply enter those 4 values in your code, and an FTC block is even provided for this. Simply type in the 4 values into that one block. You will find a sample op mode in the SDK called Utility Camera Frame Capture. The comments in that op mode describe a procedure to collect these lens intrinsics, performing the camera calibration. Once you have those values and you try them and they're working well for your robot, we invite you to share that data at FTC-community. This is a crowdsourced effort for teams to share their hard work in creating lens intrinsics for their camera. On the other hand, if your team did not collect the lens intrinsics or does not care to go through the camera calibration process, you are very welcome to go to that same website and make use of lens intrinsics that other teams have shared. You may even find duplicates with similar values. You're welcome to try all of them and find a set of values that works well for your camera on your robot with your game strategy. As a teaser, this slide gives an image of the front and back of a global shutter webcam, which is an alternate to the common rolling shutter webcam that many teams currently own. Some teams may find this type of camera of interest for the CENTERSTAGE season. You are invited to research this type of webcam. Finally, we will discuss using Pose to navigate your robot. The sample op modes give driver station telemetry like this, shown on the right-hand side of this slide. It includes Pose with XYZ position and pitch, roll, and yaw rotation. It also includes RBE for range, bearing, and elevation, which are calculated extensions of Pose. This is a lot of data to present on a small screen, especially if the camera sees more than one April tag. Next, we will learn what these numbers are, and then we'll come back and look at this slide again. To review the definition of Pose, it's a combination of the relative position from the camera lens center to the April tag center and the orientation of the April tag in the camera's reference frame. Position again is expressed as X, which points to the right when you're looking outward from the lens. The y-axis points straight outward from the center of the lens, and the z-axis points upward. Orientation is pitch, roll, and yaw, which indicate rotation about the X, Y, and Z axes in that order. How to read these numbers in your code? These green blocks provide the position and orientation values for the estimated pose. You can see the green blocks are labeled ftc-pose.x, .y, .z, and for rotation, ftc-pose.yaw, pitch, and roll. As with tag ID code, pose data is usually retrieved inside a for loop, either for immediate processing or to be stored for later use. These are the Java versions of those same green blocks from the previous slide. You can see ftc-pose.x, y, and z, ftc-pose.pitch, roll, and yaw. On this screen, these values are being assigned to temporary values. For example, ftc-pose.x is being assigned to my tag posex, which is declared here as a variable of type double. You may use these fields for telemetry, for calculations, assigning to a variable, any purpose that you wish. The calculated extensions are optional values provided to you by the STK in order to save you a lot of trigonometry that you might have to do on the regular pose values. These are for your convenience only. Range is the direct point-to-point distance in 3 dimensions from the center of the camera lens to the center of the tag. Again, range in 3 dimensions from the center of the green star to the center of the yellow star. This is a linear distance measurement. Bearing is the angle that the camera would turn through, left to right, to point directly at the tag center. This is an angular measurement. And elevation is the angle that the camera must tilt up or down to point directly at the tag center. This also is an angular value. How to read those calculated extensions? Here are the green blocks available in FTC blocks. The first one is ftc-pose.range, .bearing, .elevation. In this example, the green blocks are assigning their values to the purple blocks on the left as variables. ftc-pose.range is being assigned to a variable called my April tag range. These variables can be used later in your op mode. This is the Java version of the previous slide's blocks. Again, FTC pose.range, bearing and elevation, with each of these values being assigned to the variable on the left, declared here as type double. Now we can study the sample op mode telemetry again, hopefully with a better understanding. Here, there were 2 April tags detected in the camera's field of view. Each cluster of data gives the tag's ID code and name with its pose and extension values. The first tag here has ID code 9. The tag's name is blue audience wall small. The position component of its pose is listed here as XYZ in linear units of inches. Pitch, roll, and yaw is the rotation component of pose. These numbers here, by the way, are near 0, and this indicates that this particular tag is close to parallel to the face of the camera lens because they are near 0. And the third line gives the calculated extensions, range, bearing, and elevation. Note that the first number is in the units of inches, the other two are in the units of degrees. The second tag being recognized at this moment by the camera is ID tag with code 10. Its name is blue audience wall large, and here's the pose, XYZ, and PRY values, and the calculated extensions of RBE. At the bottom of the telemetry, the sample op modes give you a legend, so you can remember these terms. PRY is pitch, roll, and yaw, which are rotations about the XYZ axes, and RBE for range, bearing, and elevation. We mentioned earlier that there are 2 sample op modes that can actually navigate and drive your robot. These are simple examples with very good commenting, which we encourage you to study in order to see how the commands you've learned in this series of slides can be applied to actually navigating your robot. Use the first op mode if your robot is a tank drive robot, namely the left side wheels and the right side wheels are controlled independently. This op mode is called Robot Auto Drive to April Tag Tank. The op mode will simply drive directly towards an April tag that it recognizes in the camera's field of view. Use the second op mode if your robot has a holonomic drive, namely 4 omni wheels in a star pattern or 4 mecanum wheels. This op mode is called Robot Auto Drive to April Tag Omni. Lastly, we mentioned other VisionPortal topics that we did not have time to cover here. We did not cover the detailed camera calibration procedure to generate your lens intrinsics. That procedure is described in the sample op mode. Second item, we did not talk about how to create an April tag custom library with the builder. For the third point, we did not talk about managing CPU resources and USB bandwidth. Vision processing is expensive, using much CPU capacity and USB bandwidth to process millions of pixels streaming in from the camera. The SDK provides over 10 tools that you can use to manage these resources, allowing your op mode to run effectively. For the fourth bullet point, we did not cover webcam controls. This gives you the ability to manipulate the images as they come in from the camera before those images are processed by the April tag or TensorFlow processors. You can control the exposure or brightness of the image, its gain, its auto exposure priority, focus, pan, tilt, and zoom, and white balance. For the fifth item, we did not discuss the details of how to switch between two cameras. This is described in the sample op modes of those names. For the sixth point, it's a very exciting feature in this year's VisionPortal, which is the ability to have more than one VisionPortal active in your op mode while it's running, including the ability to have multiple previews on your RC device. So, for example, could an op mode run two VisionPortals, each using switchable cameras? The answer is yes. You could, under that arrangement, have 4 webcams on your robot. Keep in mind, of course, to do that, you will be making heavy use of this third item, managing CPU resources and USB bandwidth resources. The last item is for advanced teams. It's the subject of field-centric navigation, which we will address a little bit more here in the next slide. If you know where the tag is on the field from the metadata, and you know where the tag is relative to the robot's camera, then you could determine where the robot is on the field. For advanced teams, VisionPortal and other tools like odometry and other sensors could allow a robot to navigate in the FTC field coordinate system shown here. Namely, if you are standing in the red Alliance station looking at the field, the positive x-axis extends to the right from the center of the field, the positive y-axis extends away from you, and positive z extends upward. This concludes our overview of the FTC VisionPortal. You are welcome to send comments and questions to the Discord. The handle is Westside on the SoCal FTC Discord, or send emails to the address shown on the slide. Best of luck this season, and we look forward to seeing what exciting things you can do in the CENTERSTAGE game.